Good evening. This is a very short presentation of the full scope of the work that I have completed today. I can say with confidence that I have completed all the aspects of the work that I wanted to complete, and the results are very, very good. As you can see, I think you are familiar now with this screen. In the longer video you saw this, but of course this is not the same file. I restarted everything from scratch. As you can see, the name here has changed. So this is the implementation tree, but actually with many more. So what kept me away from finishing it earlier, it was the fact that I was not able to reverse the z-score of the prediction, because of course you know that I explained to you last time that when I did the work I had to shift the system of coordinate into z-score to reduce the stretch between the higher values on the table and the lower values. And now I had to apply the z-score. I explained to you last time that the z-score are just rewriting the distribution of the data points, but by using the probability of each data point. So we locate the probability and we rewrite the distribution, so it is like the measurement of the separation between each data point to the mean of the distribution, measured in the unit of the standard deviation. So you take like the whole distribution of the data, so the range of the data from the lower to the higher, you plot it as a distribution. Now you work out the mean of this distribution, then you measure the distance of each data point with respect to the distance that separates each data point to the mean in unit, and that unit is your standard deviation, and that is called the z-score. So you apply that technique in order to make the stretch between the lower and the higher value smaller, because you don't want the higher value to influence your prediction. So after you do that, then you have the z-score, then you can do everything in z-score, but you have to revert back to the old system, because in this case, for example, we are predicting the indices. The number should say something, not the z-score, but the numbers. So I had trouble reverting that. It took me some time, and also I had a rough weekend. On Friday, I caught a flu. I think you can hear in my voice. I was sick. Saturday, I didn't even sit on this computer, and yeah, Sunday I was very sick as well, but I'm better now. So, and today I was able to go through and finish everything. So the beginning is the story that I told you last time. We import all the modules, we import the data. These are the data, and this is the main problem we found the last time, that the data missed too many entries. Every time you see none, it means that there is nothing there. So if you open your Excel sheet, there is nothing. So, and you do have the data spanning from 1960 to 2020. Now, the first thing that we need to do is to solve the missing problem, as I explained to you. Last time I tried to use a technique that is row-wise missing, meaning that I solve the missing by a column-wise, by filling in the column. But I thought each indexes evolve on its own. So each index is a different entity. Why should I fill the missing with the row? So I did it by column, by row. So this is why I wrote this other function where I fill by row, then I fill the missing with the First of all, I'm counting the missing. So I count the missing, I plot the missing in terms of in a row. We have 1,443 rows for each spreadsheet of the data, and these are the number of the missing per row. Remember, we have this much row, but we have only 66, I think 60 something, 60 from 1960 to 2020 is almost 61 years, because you count from 1959. So for all the 61 years, bear in mind that you have 4 years that are just some kind of coefficient and labeling and so on. In all the 61 years that you have here, you find that there are some rows that misses 60, almost 61 as well. So those rows are useless. We should remove them, because this indicates, each point indicates how much a row is missing, and here you have the row label. So which are the rows, remember, are indices. These are the indicators. So each row is like export income and so on. So these rows are missing stuff. So that's in terms of column. This is how much a column is missing. For example, if you take a column as a year, a specific year, like 2020 is missing about 1,200, 1,000, more than 1,000 data. So for 2020, we almost have nothing. And then you have also these other data. So the first thing that we have to do is to drop every row that doesn't have more than 12. First, we cut the number of years from 93 to 2020. So we take almost like 27 years. So we cut to 27 years. And in these 27 years, we require that each year must have at least 12 entries. So 15 entries. So we impose that condition, and after dropping all the rows that are redundant, that have no enough data, we are left with each country's. For example, South Africa is left with 1,015 rows, Nigeria with 864, Tanzania with 984, Ethiopia with 924, and the DRC with 836. But we're doing the study for everyone. So in order to uniformize the thing, we pick the rows that are in the DRC, because it is the country that has the lower number of rows. We make the intersection of each country's row, so that we have the same amount of row. We make the intersection of the row. So we have to put all the row together and find only indices whose label are present in every datasheet. By doing so, we found 159 indices are still available to us. So these are the 159 that we will use in our study. And then we go. Last time we had fixed 55, so this time, because I've extended the number of years and then changed the criterion a bit, we have more. So then we go now in the next phase. After uniformizing the data, we still have the missing. We work out the missing. You see now in rows we have at most 18 missing, not more than 18, and this is spread. And in terms of column, only 2000 has more data missing, 2020 has more data missing, but the other years have a better spread. So then we go below. Now we try to fill. We can fill either row-wise or column-wise. So we fill column-wise with the average, and then we have the data which are completed. Now, I explained to you that the data have a huge gap between them in terms of values, So I apply the z-score, which I explained to you in the beginning. So I write a function here, a method, as we call in computation and programming, a method that works the z-score of each row, because each row is a specific index. So I work it by row now, and I write also the method that reverses the z-score. As you can see, when I apply this method, I also want to keep the statistical value, because before I like the mean and the standard deviation, because if I lose them, I won't be able to reverse this. So that is why I split out here the statistical value and the table of the data. So when I do the reverse, I write the method that do the reverse. The reverse is just simple algebra, and what I get is that when I do the z-score for the data, if I take this table, which is the table that I have reversed the calculation that I did here. This is the z-score table. When I reverse it, you can see that the values are pretty much the same as the one that are in the original table that I filled. So you compare, the method is definitely working. So that is the proof that when we will use to refer the prediction, it will be fine. These are the z-score table. As you can see, here you have the value, very big values. There we have like the 1, the minus, and so on and so on. So that is what we've done here. And then the next thing, I do this for all the data table. I work out the z-score. As you can see now, I want to plot the distribution, but because I have 20, almost like 6 times 7 times for 28 column, so I split them in 4 because I want to plot this. And when I plot, this is the distribution of the data. Now here the appearance of the spread between the data, you can see the lowest value is -1 and the highest value is 10 to the power 12. This is Ndiako. You find this all over the place. Like for example, in South Africa, the highest value is 10 to the power 14. So you cannot make prediction with some value like this. When I apply the z-score and the distribution are much more reduced, you have the lowest value which is around -4, -3 something, and then the highest value is +6. So this is more bearable. So after this, I check the missing as well, because sometimes I had some funny games playing me where the z-score were after the z-score I had the zeros, because some standard deviation were 0, like when the distance is 0, then the z-score will throw you an answer. I sort that out. Now this is now the data. I split it into feature engineering. What is feature engineering? This is the thing. You want to do a regression model where you split the data so that you have the independent variable that help you to predict the dependent variable. So the last column, the year that you want to predict, is depending on the previous. So the previous year is your independent variable. So I split this like that. So this is feature engineering. I take in the data table. I say, okay, take all the column going from the second all the way, because the two first is indicator name and indicator label. I don't need them. Take going from the second column all the way to the end, but this will be my by feature will be just you remove the 3 outer column, you keep the 20, it was 25 column, so that's why I call it features 25. So I have 25 years of data, and I want to predict the 26, the 27, the 28 if I can. So this is what I do, and I have that. Now let's go. Now here I reframe the data. Why am I reframing the data? Because you will see that the data that we have has too much correlation between them. What is correlation? It is like the data, they agree with each other to have like some kind of collaboration. We don't need that. They are like witnesses talking to each other. So if you have witnesses talking to each other, then your case is broken. So in that case, we need to destroy correlation. In physics, in geometry, we call this autonormalization. So we rotate the system of axes such that the axes make 90 degrees between them, because then they have no correlation. So I do this, and you will see this when we plot the correlations. So for example, the original data each year and the next year, you see, for example, the year 1993 has very strong correlation, because these are the values. 1 is a very strong correlation and 0 is no correlation at all. As you can see, already from 0.2 0.5 is very high correlation, in particular in the science like psychology. 0.3 is already high correlation, but like already you see where you see reddish is very high already. So this means that this type of correlation is unwanted. Like you see, for example, 1993 still have very strong correlation up to 1999. So we don't need this. So this all patch of reddish, this means that there is too much correlation. You have to destroy this. To destroy this, I do the orthonormalization. When I do the orthonormalization, you see what is happening. What's happening is that there is no more correlation between any dimension with the next, because I've changed the system of axes, but I still have 27 years. And why there is red in the middle? The red is the autocorrelation, meaning that each value is correlated to itself. Like you, Naomi, you are correlated to yourself. Everyone is correlated to themselves. So yeah, that's why you get that diagonal is where the value is, while elsewhere is 0. You can see 0 elsewhere and 1 in the middle, which is good. So now that we have this, let's move. Our next move is to split now the data into dependent variable and independent variable. Dependent variable, I call them X. Independent variable, I call them X. Dependent variable, I call them Y. So this is why I write this method. I say, okay, separate this, and we do that. After I do that, now here is where I build my first neural network. The first neural network is the one I will use to predict the case of Congo. This network is dense. It is made of, outseeing is, I have 25 entries. So I have like 25 neuron, 25 bubble, and then I put these 25, I inject them into 60s. So I have another row of 60 neuron, so which is the 60. Then I take them out, I bring them to the row of 10, and then I bring them out one by one. So when I do this, I predict, when I train the neuron, I've split the data. I didn't show you that. I've split the data already into two categories. What we call, one we call the training set, and the other the testing set. So the data is made of 159. So I take 75% of it, which is 119. 75%. That's 119 rows I train with the network, and the 40 left I test with the network. So to see if the training, because when I train, I give to the network the independent variable, and every time it brings the value, it compare it to the dependent variable, that is the training set, and it learn. If it was wrong, it's correct, it goes back, it's correct, and it comes. So this is where you get this loss function. It is like I'm learning. In the beginning, my prediction are very bad, the loss is very huge, and then the loss decrease. As my knowledge increase, the knowledge of the network increase, the loss decreases. So because it is like ignorance decreases with the knowledge, so the loss is like the ignorance. So after that, I train the second network. This one has 40 and 5 in the middle. You know how to read the network now, so you will know. So as you can see, every time we learn, the ignorance is decreasing. That's why you see the value of the loss is decreasing. You will see the curve anyway. Don't think that I'm going fast. You will see the curve. And the same as for the third one, network that concern Nigeria. The fourth that concern, it has 55 and 1. That concern South Africa, and then the last one that concern Tanzania. So this is what happened. You see the table of loss. It is like loss and loss values. This is epoch meaning that the number of cycle of the time of learning. It has learned 57 times, and this is what it's got. 58 times, this is how it is losing. You can see the values are decreasing as the number of epoch increases. So let's plot this epoch so that you see. This is the learning curve. Ignorant in the beginning, at the beginning, epoch 0. Epoch is like time frame, 0. And as you grow up in the learning, the ignorance is decreasing. That's why you see the loss is decreasing. The same, this is for DR Congo, the same for Ethiopia, the same for Nigeria, the same for South Africa, the same for Tanzania. These are very, very good learning curve. Check in any book of machine learning and deep learning. This is very, very good training of a neural network because it is learning actually. And you can see that for Congo, it learned quickly, 60 epoch, that's enough. For Ethiopia, 140 epoch. For Nigeria, 250. For South Africa, 120. For Tanzania, 120. So we get that. Now, let's work out the root mean square. You know what is the root mean square. So the root mean, the mean square error. The mean square error, so you take the error between the value and then you work. So the mean square error for all the network is almost the same, 5.5 and so on. But I prefer more a more method to measure, which is the root mean square. So these are the root mean square that we make. I don't like this value. I should return the thing again. That's fine anyway. So after that, so let's now see what is the prediction, the difference between the values. So these are the visual, these are the data points for 40 of we use to test the data, and these are the red are the predicted value. As you can see, for example, this one on row 0, it is spot on almost. This one has a bit of difference and so on. You see, for example, this is a miss. This is like 1 and that is 2 point something. So normally this one will appear like it is a miss. This is what cut the percentage. This is fine. This is a miss as well. This is fine because the distance is close to the, is lesser than the root mean square. This is fine, this is fine, this is spot on because the 2 points are almost sitting together and so on. So this is how you read this graph. So this is like the reddish one are the predicted value and the blue are the real data point. The difference, the distance between, you look at the point vertically because each points are sitting in the same row. This is the row, the label of the index. So if you see the distance is bigger than the root mean square, which is for Congo, it is 0.7, which is not good actually. I will correct that. I will train again, maybe it gets to lower, or yeah. So if you see the distance is bigger than 0.7, then the system will say that the training is not, the data didn't hit, it missed. This hit, this is hit, this is hit, this is hit, 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 misses, hit, 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 miss, hit, 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 hit. You see, you train. This is how we work out the percentage. And you look for other countries. You can check this DRC, you can check for South Africa and so on. I'll send all of this to you. And now let's compute the efficiency of our algorithm. The efficiency, you can see when you do the calculation, you check the margin of error. The algorithm predicts 80% accurate for the DRC indicator, 75% for the Ethiopia, 80 for and so on. At one time I trained, there is one country, Tanzania, it's 97%, because you know, it is like they say, the more you learn, the more you know. So if you train several times, maybe it can happen. You can also change some other stuff. So let's look at the other things. So now let's try to predict for 2021. So we take the model. Remember the network that I built up here. I'll go back to app. You see, I call it model 2. Model 2 is related to Ethiopia. Model 1 is related to DRC. Model 5 is related to Tanzania, and so on. So you will see that I'm predicting for the DRC for 2021. I'm predicting what happened. I give it the feature. I give it for 25 years. For 26 years for it to predict me what is going to be the data for 2021. So I give it this value and it predicts. After I predict, I patch up the things together so that you get the data in the shape of the table. And this is what we have in terms of z-score. As the predicted value for 2021 is this. Now let's go look at Congo. For 2020, these are the values. Now for the predicted value, this is. For 2021, Congo in terms of ore and metal exports in percentage of exportation, it will expect to export 13.10 and so on. So you can see that the value is decreasing from here, from this 2020 to 2020. If the country doesn't export more, what it means that importing will be lower as well. So you can see that importing is lower. Last it was this, and now it is gonna be down. So the population in DRC, the population between the age of 60 to 64, last year it was 2.7 something. Now it is 2.4, and you see the age and so on. So let's look at I'm looking at South Africa. I was talking about DRC. So let's look at SA is South Africa. So let's look at South Africa in terms of the tail, the export of good constant in dollars. So in this is almost in trillions of dollars. So the export is good, but it went down a bit last year, maybe because of Corona. And you can see also the part-time employment in South Africa went down as well because of maybe Corona. Now, what do we predict here from last year to this year, you can see that the trend is still not doing good. The exporting of the products goes down as well because there is no work because of the COVID, and the part-time employment has gone down, more joblessness. Here we were like 114, now we are 99. We have lost like almost 114. I don't know which unit they use. And of course, they say percentage per total employed. Yes, percentage per total employed. Okay, so it is 1%. It goes like from to lesser. Okay, so then you have gross domestic saving. Gross domestic saving is gone down because you have no employment, so people won't save because they are not anymore. So now, incidence of malaria, more people sick, no less people sick, which is a good news. And current education expenditure, how much money is spent on education? Less money than last year. So you see this type of prediction. I've displayed to you a few of these table, all these table, at least 10 column, 10 row per each table per each country, so that you look at how it looks like. Okay, let me just go back slowly so that when you look at the video you are able to see. The first thing, I go back to South Africa. Here I present you the raw data before prediction. Here I present you the top of the prediction. You can see and this is they correspond, and you can read off the value for 2021. Here I present to South Africa the bottom. This is the first 5 rows. This is the last 5 rows. And you can see the predicted value. Predicted as always predicted. This is the data that I filled, removing the empty spaces. So that's why I call it filled. And you can always compare. And you will always see that 2020 here is this previous column, and now we are 2021. I could predict for 2022 too. I just have to go to 19 from 19.5 and then I'll put. But you predict with involving the prediction of this year, so you are more likely to make more error. So this is for South Africa, and we go to Tanzania as well. I give you the 5 top rows, and I give you the 5 bottom rows for Tanzania. I give you for Ethiopia 5 top rows, and Nigeria, and 5 bottom row with the prediction. And I give you for Ethiopia 5 top rows and 5 bottom rows. And I give you for the DR Congo to close 5 top rows and 5 bottom rows. So this is it, and this is the work. So what are the things that we will use in the article? These are the things that are very important to, of course, the table if they want. If you want, I can put them as, I can make them Excel sheets, but that we will see. And this is something that you will have to present in the paper, because this is the prediction. And what? This is the learning curve. This is something you can present in the paper as well with illustration. What else can you present? Of course, the network you will draw and you will explain. The correlation map, why we did this is always important because it helps for anyone who read the paper to understand that you have a full understanding of what you're doing. And of course, these are things that they make life beautiful, because you present something like this, they see that you really have you master your understanding of the topic. You understand what you have to do in order to get everything right. Okay, and of course you can also mention the missing of the data. Data manipulation is the most difficult part. It takes more time, it consumes more time. You can see how many days did I spend and how many days I've spent to build the final product. So that is it, and I am done for now. So I'll go and take myself a shower, then get ready to sleep. But in any case, this is it. So feel free to write to me with suggestion of what you think should be on the article. And I don't like your Microsoft Word, but I don't have energy to redo everything in LaTeX. In any way, I will use your stuff. So I'll try to put my contribution and then I'll send everything to you. But right now I'm sending you the video. I'll put it on my YouTube anyway. And I'm sending you the notebook. Okay, that is it. I can send you the notebook as raw like this. You will open it with Google Colab. But if you don't want, I can send it to like I sent the last time. I will do the same. Okay, that is it. So have a good night and God be with you.